Alright, 2.5, we're going to look at inverse functions. So in general, when we start to talk about inverses, we know that inverses essentially undo what another function does. Okay, so you guys have seen some inverses of each other. The inverse addition to addition is subtraction. The inverse to multiplication is division. So we will explore inverses. Before we get too far in, what I would like to do is I would like to look at a one-to-one function. So 1, 2, 1 functions. And we're going to look at one-to-one functions in a couple different ways. The other thing I'll mention is that we will sometimes abbreviate it as 1-1. But when we talk about a one-to-one function, what we mean is that no two ordered pairs have different first coordinates have the same second coordinate. And if that happens, we say that then the function is one-to-one. So what we're essentially doing here is we're not looking to see if the x values repeat. We know that shouldn't happen because we called it a function. But what we are doing is looking to see if the y values repeat. If the y values never repeat, then we say we've got a one-to-one function. So I thought what we would do is start by looking at some examples. So is this one-to-one? And the first example we are going to look at consists of three ordered pairs. -1 pi, 0, 3.14, and then the last ordered pair is 1, 22/7. So if this is a one-to-one function, notice all the x values don't repeat, so it's a function. And now we want to check to see if the y values are the same. So we have pi, 3.14, and 22/7. Now I'm guessing if I looked at my classroom, if you guys were in class with me right now, about half of you would say, yep, it's one-to-one, and the other half of you would say, it is not. If you think about pi, if you punch pi into a calculator, you get things like 3.14159, and it actually goes on forever. That is not the same as 3.14, which is not the same as 22/7 either. If you take 22 and divide it by 7, 22 divided by 7, my calculator spits out 3.142857114. Again, none of these numbers are the same, which means that this is in fact one-to-one. One-to-one. If we look at the second example, which consists of the ordered pairs 2, 3, 1, 5, -2, 6, and 4, 5. If we want to decide if this is one-to-one, again, we're checking not the x values, but here we're looking at the y values. And here we can see that this is not one-to-one because the value 5 repeats. So this one is not one-to-one. Now, you might be thinking, is there any other way we can check by having to look at a whole bunch of ordered pairs? And the answer is yes. We can visually check if a function is one-to-one using the horizontal line test. Okay, so the idea is sort of the same as the vertical line test, except we're putting in horizontal lines, lines that go from left to right. So, if we think about putting as many horizontal lines as we want, then we're checking to make sure that none of the horizontal lines pass through more than one point. So if a horizontal line does not pass through more than one point, then the function is 1 to 1. Okay, that's what we mean by the horizontal line test. So horizontal lines, again, they go from left to right. So let's go ahead and check some graphs you guys are familiar with. Consider y is equal to x squared. Y is equal to the square root of x. And y is equal to x cubed. I'm going to give you some really rough sketches here. Hopefully you're fairly familiar with what these are starting to look like. So if we go and start looking at each of these, for any horizontal line that I put down, so notice this bottom horizontal line I drew in red doesn't pass through any, and if I drew it on the x-axis it would pass through 1. But if we look anywhere else, it's going to pass through 2 points, which makes this y equals x squared, not 1 to 1. When you look at the square root of x, again, start putting some horizontal lines down. At the x-axis, it only passes through 1 point, and any other one I draw will only pass through 1 point. So this one is 1 to 1. And then last but not least, if we look at y cubed, notice that any line we put only passes through one y value. None of the y values repeat. So this is 1 to 1 as well. Okay, last but not least, let's look at a way that we can algebraically check. So algebraically, we check to see if a function is 1 to 1 by seeing if f evaluated at x sub 1 is equal to f evaluated at x sub 2 implies x1 is the same thing as x2. So some of you might be a little curious to see what this means. So let's check h of x is equal to 5x squared. So if we want, we're going to look to see what is h evaluated at x1. So we'd take 5 and then x sub 1 gets squared. And we also need to look at h evaluated at x2, which says 5 times x sub 2 squared. So we will set h of x1 equal to h of x2, or 5x sub 1 squared, and we set it equal to 5x sub 2 squared. Now, these little subscripts are just a way to represent different numbers. So, we'll start by dividing each side by 5, and we would be looking when x1 squared is equal to x2 sub 2 squared. And if we want to keep going here, then we would square root each side. But don't forget, you get a positive and negative root. So x1 would be equal to plus or minus the square root of x sub 2. So we get two different values. So x1 doesn't necessarily have to equal x sub 2, which means that this is not 1 to 1. Okay, if x1 always had to equal positive x2, we would say it was 1 to 1. But because it could be equal to negative x sub 2, then we say our function is not 1 to 1. We're going to look at another one. So check if k of x is equal to 3x is 1 to 1. So we're going to set k of x sub 1 equal to k of x sub 2. When we do this, we're looking at 3 times x sub 1, and it's equal to 3 times x sub 2. We would divide each side by 3, and notice we'd get x sub 1 is equal to x sub 2. So this implies x1 equals x2, and so k of x is 1 to 1. Okay, so hopefully you have a pretty good idea of what it means to be 1 to 1, both graphically and algebraically, and how we could even test with ordered pairs. We can also talk about the inverse of a 1 to 1 function. So the inverse of a 1 to 1 function is found by switching x and y. Oops. And we'll look at a process to do this a little more in detail in just a couple moments. But the notation we use is f, it looks like to the minus 1 of x, but we read it as f inverse of x. Okay, it does not mean 1 over f of x. Don't confuse it with negative exponents. This is how we represent the inverse to some function f. So let's consider the function h of x. And h of x, or h, is equal to 2, 1, 3, 4, and then the last ordered pair is 4, 0. So the first thing I want to know, is it 1 to 1? And the answer is yes. It's 1 to 1 because none of the y values repeat. So the next thing we want to do is find h inverse. So if we want to find h inverse here, we find it by switching values of x and y as stated right here. So our inverse should be the ordered pair. Instead of having 2, 1, we now have the ordered pair 1, 2. Instead of having the ordered pair 3, 4, we have 4, 3. And instead of 4, 0, we now have 0, 4. So we swap the x and the y values. The last thing that we can do, and I'm going to use a little bit of space right here, is I can ask us to find h of 3 and h inverse of 0. If we want to find h of 3, this is asking us to go and look at the h function right here and look at what happens when x is 0. What's the y value we get? 4. When we look at the inverse function, h inverse of 0, plug in 0 for x. What's the y value you get? 4. We could have looked at other values. I chose these just so you could get an idea of how you evaluate ordered pairs. Graphically, inverses are reflections over the line y equal x. So that's something you can look to see if it's a mirror image. This is something that I would like you guys to look at page 240, and you can read more about this. What I would like to focus our energy on is how we can find inverses. And this is using the switch and solve method. And here's how we start it. So the first thing that we do not the Q thing. The first thing is if we have function notation, we replace it with a y. So replace f of x, or g of x, or q of x, whatever of x. So replace f of x with y. The next step is to switch or interchange x and y. Anywhere you saw an x, you put a y. Anywhere you saw a y, you put an x. Then we solve for y. And then the last thing that we do is replace y with the function notation, our inverse notation. So we replace y with f inverse of x. And the last thing we really should do is you should verify domain and range. Okay. So as we look at some examples, we are going to find the inverse, find the inverse for, and we may do one right now and we might do a couple extra in class. H of x, which is equal to x cubed minus 5. So when we start thinking about our steps, we said we get rid of the function notation. So we have y is equal to x cubed minus 5. After we've done that, we interchange x and y. So we have x is equal to y cubed minus 5. And lastly, we want to start solving for y. So we would add 5 to each side. X plus 5 is equal to y cubed. To get rid of a cube, you would have to take a cube root. So we have the cubed root of x plus 5 is equal to the cubed root of y cubed, or the cubed root of x plus 5 equals y. But it's not really y, it's, in this case, h inverse. So we have h inverse of x is equal to the cubed root of x plus 5. We shouldn't have any issues with the domain and range here, and that's because they're both all real numbers, are infinity, negative infinity to infinity. This next example that we look at is y is equal to the square root of 3x minus 1. So we don't have function notation, so we're going to start by interchanging x and y. X is equal to the square root of 3y minus 1. And here we switched into x and y, so now we want to start solving for y. So we would square each side to get rid of that square root. So we have x squared is equal to 3y minus 1. We would then add 1 to each side to isolate y. X squared plus 1 is equal to 3y, and divide each side by 3. So we get our inverse, y inverse, is equal to x squared plus 1 over 3. And one of the things that we can talk about, so we can talk about the domain and the range for y. If we look at the domain, my claim is that it should be from 1/3 to infinity, because when x is 1/3, we have 3 times 1/3, which is 1. We'd subtract 1, we get 0. Any other positive number will make this square root. It'll make this square root positive valued, which is what we wanted. And then when we talk about the range, the square root can give us values between 0 and infinity. So this was for y. When we look at y inverse, the domain and the range, what we'll notice is that they swap. So the domain, my claim, is from 0 to infinity, and the range is from 1/3 to infinity. And the reason that the domain and the range switch from the original function is because what did we do? We interchanged x and y. Well, here's your x values. They now became our y values, which represents the range down here. Our y values became x values, which represent our domain up here. The last example that we'll do is finding the inverse. So find f inverse for f of x, which is equal to 2x minus 1 over x minus 6. So we start by writing y is equal to 2x minus 1 over x minus 6. We interchange x and y. So x is equal to 2y minus 1 over y minus 6. And can you guys see what's going to happen? So we're going to multiply each side by y minus 6 to clear the fractions. And as we distribute, you'd have xy minus 6x is equal to 2y minus 1. So here we want to move all of our y terms to one side. So I'm going to subtract 2y from each side. So I've got xy minus 2y minus 6x is equal to negative 1. I'm going to move this 6x to the other side. So we have xy minus 2y is equal to 6x minus 1. And what do you notice about the left-hand side now? Xy minus 2y is equal to 6x minus 1. Do you guys see that they both have a y? So you can factor that out. Y times this quantity x minus 2 is equal to 6x minus 1. Or y is equal to 6x minus 1 over x minus 2. But that is really f inverse of x. It's equal to 6x minus 1 over x minus 2. This is definitely one of the more challenging ones, but I would make sure that you are aware on how you can do it. And the last thing that we are interested with is verifying we have inverses. So verify we have inverses. And without having to try and graph these every time, one way that we can do it is we have to check that if you look at a function composed with its inverse, that you'd get x. And if you look at the inverse and compose it with the function, you would get x as well. So I can ask you things like r f, which is equal to 2x plus 1, and g, which is equal to x minus 1, inverses of each other. So if you start, you might look at f composed with g. That means we want to take f and evaluate it at x minus 1. So we would take 2 times this quantity x minus 1 and add 1. 2x minus 2 plus 1. That's the same as 2x minus 1, which is not equal to x. So the answer is they are not inverses of each other. If we had gotten x, we would want to look at g composed with f as well.